Okay. So last week we were in the business of finding the area underneath a function, or the area under a curve, but above the x-axis and between 2 points. And our first attempt was a pre-calculus way of doing it. We divided it into rectangles or trapezoids. We picked an endpoint method, and we came up with a reasonable approximation based on 4 or 5 rectangles. It was not too big of a deal. Then we said what would happen if we were to increase the rectangles, and we said that would be great. Sure, you can take a picture of that. That's nice. And then the more rectangles you have, though, that width is going to get smaller, but your approximation is going to get more accurate. And it's not enough just to do a million rectangles. What we really want to do is we really want to do like 5 rectangles and figure out what the area approximation is, then 50, then figure out what that number is for the approximation, then 500, figure out what that number is, then 5,000. You know, we eventually want to get to 1 million and 10 million, but it's not interesting enough to know what is the area approximation at 10 million and 50 million, but rather what is the trend of that area approximation? What is that number approaching? Okay, and what we came up with was we want some sort of limit as the number of rectangles approaches infinity of the summation, that's right here, the sum, of all of those areas. This area plus this area plus this area plus this area. And we came up with this expression. There's a whole class period, so just take our word for it on that. Okay? And then we actually applied this formula to a particular problem, and we worked it all the way through, and we simplified it down using the summation formulas, and we came up with an actual number. And then we said, hooray, that took us 25 minutes or whatever. It would be nice if there was some sort of shortcut process on that. Yes?
They said to bring this to me.
Back door? Next all you need is the other side of it. Right?
Yeah.
Okay. All right. And you kind of have to take the calculus textbook and my word on this, but there is a shortcut. All right. So that area, which we had, I'm not going to write all this down. The limit as n approaches infinity of the summation. What this was is this did not give an approximation. If I said what is the summation for 1,000 rectangles, then that would be an approximation. Or even if for 1,000,000 rectangles, that would be an approximation. But when I say what is the limit as the number of rectangles approaches infinity, then we're going to get the exact answer. Okay? And that answer can be written like this. This elongated S from A to B f of x dx. And we notice, oh my gosh, that's the antiderivative symbol. And it is. And in fact, it relates to the antiderivative. So I guess I kind of, I straight up did lie to y'all last week when I said, and now for something completely, we did the antiderivative, and you're like, yeah, this is fun. We can handle antiderivative. It's just, you add 1 to the exponent, you divide, and all that kind of stuff like that, if you remember how that was. And then the next day I said, we're going to do something totally different. We're going to do the area. Not related at all. Okay, yeah, that was a bold-faced lie. Okay, it's completely related. That's the purpose, okay? This was really long and annoying and had lots of algebra, and we weren't really crazy about it, and it had lots of room for error, okay? But the antiderivative, we could just do really quickly. The only thing is, the antiderivative, we're like, what does that really tell us? Okay, is it really very useful? This is very useful, and it's great. We really get the best of both worlds. We get something that's really useful, very applicable. We're finding the area under the curve. We talked a little bit about all the different applications for that. And then we also have a really easy way of finding it. That is the antiderivative, okay? So the thing is, though, is that this expression right here with the numbers right here from there to there is called the definite integral. And And we don't necessarily know how those numbers kind of fit into everything. That's the very brief lesson that I'm going to tell you today. What we do know is the indefinite integral. That is, if I have something like the antiderivative of f prime of x dx equals f of x. Technically, I can say f of x. We'll see. This is what we already do know. Now, I never wrote it in this fashion, but see if this makes sense. What I'm saying is, take the antiderivative of the derivative, and that's going to give you
The derivative.
not the derivative,
Or
obviously,
the original
the
function.
original function. Yeah, that's what we call it f of x. But then we also had that plus c right there. Okay, so I'll tell you now how does that relate to this. So assume that this right here, this little f right here, is itself the derivative of a function. Okay, so you might be like, well, what would it be? Because it normally would have f prime there. Let's just say that there's a parent function, so to speak. It's not really a parent in your algebra 2 sense, but there's a function above f. Okay, so we'll call it capital F. All right. Assume that there's a capital F function. Okay, and if you take its derivative, so big F prime of x equals little f. That's a prime marker. So if that's the case, this is how we think about those A and B. The antiderivative of little f is big F of x, and then evaluate that, that's what this bar means, x equals A and x equals B. In fact, if I wanted to be real technical about it, in fact, I probably should put this. It's f of x plus c evaluated at x equals A to x equals B. And you're still like, okay, what does that mean? Okay. That means you plug in B, so big F of B plus C minus big F of A plus C. That's what the evaluate bar means. And so if you notice, if I distribute this minus, I have f of b minus f of a. And plus c cancels out. So c minus c is just gone. So here's the short version. It's called the fundamental theorem of calculus. The integral from a to b of f of x dx equals capital F of b minus capital F of a. That one also doesn't seem to want to put it. And that's also obviously going to equal the area under the curve, under f of x, but above the x-axis, and between a and b. problems so we can see what's going on.
Did you get a haircut in this regard?
I did. Thanks for that.
Nice. Shave on side.
Alright, so number one is a great problem because we're going to find the area under the curve, but the curve is something really basic, it's just a line. So what we'll also do is, as a way of checking it, this actually is a geometric shape. It's a trapezoid. So we'll be able to use that as a check. So we actually can find via pre-calculus mechanisms the exact area, okay? But we're going to try with the calculus way. Alright, so here we go. So we shall now, via the power of calculus and the definite integral, find the exact area under here via lots of rectangles there, and looking at that trend, okay? So, what we want to do is, what's the antiderivative of x? It's not 1, that's the derivative. You're close, I heard a plus c.
Is it x over 1?
No, it's currently x to the first.
So x2
X
squared
squared
plus c.
divided by 2. Now we're kind of
Plus
getting,
C.
I know, it's still Monday, so yeah. Alright, now I could put plus c here, okay? However, if you remember, we said is, we're going to end up evaluating it from x equals a to x equals b, and so if I put a plus c, and I put a plus c, and I'm going to subtract them all out. So ironically, after all those, warnings to always put plus c, if it's the definite integral, that definite meaning it definitely has numbers, actually means it's definite, it's defined. Alright, so if you've got the numbers there, then actually you don't need the plus c, okay? But if it's the indefinite, where there's no numbers there, then absolutely you have to put the plus c. So x squared over 2, this is evaluated from x equals 1 to x equals 4. And what that means is, you plug in 4 for here, so 4 squared over 2, minus, you plug in 1. So 1 squared over 2. So yeah, you start to see how fast this is. So 16 over 2, that's 8, minus 1/2, so 7.5. That's the calculus answer. Let's look at the pre-calculus way. It's a trapezoid, so 1/2 base times, 1/2 the sum of the bases times the height. So this base right here was 1. This base right here is 4. And the height between them, 1, 2, 3. So that's 5. 5 times 3 is 15. Half of 15, what do you know?
Crazy.
Are you a believer?
No. I don't want to be a peer man.
Okay. Alright, well you grow up, little boy. Alright. That doesn't want to work today, so that's fine. Now we'll do something that cannot be easily solved with trapezoids, right?
That is this
So, it's kind of curvy, but believe it or not, we're going to get an exact answer to this. Okay, so here we go. So, apply our antiderivative skills. So, antiderivative of x squared
x cubed over 3
over 3 plus
4x squared
over
4 over 2
over the 2 plus
6x over x.
no, not it would be 6x to the first over 1.
Yeah.
But
And
You don't need to do that. I'm going to put that whole thing in parentheses, and then I'll say evaluated from x equals -3 to x equals 0. Now, I'm writing that for us because y'all are beginning calculus students. Most college professors and calculus students would literally just write -3 to 0. That's the more standard way to do it. And now that I've told you that, that's also the way that I'm going to do that. So we would plug in 0, well that's great, 0 cubed over 3, that's 0. 4 times 0 squared over 2, that's 0. 6 times 0, okay, so that's 0. That's not too bad, that whole first part there. Minus, and that's why I put the parentheses in here, so -3 cubed over 3 plus, I'm going to do a little bit of simplification, that 4 over 2 will reduce this to 2 times -3 squared plus 6 times -3. So we've got a negative out front, -3 times -3 times -3.
That's going to be negative
-27 divided by 3.
negative
9. 2 times -3 squared, so -3 times -3 is +9, so 2 times 9 is 18. And then, oh, that's interesting. 6 times -3 is a -18. Okay, so those actually cancel. Are you telling me that the answer there is 9?
Whoa.
Wow.
That's crazy. Is that the...
It is.
Yeah, no, it's fine.
All right. So that being said,
Wait, that's it?
let's see. Yeah, that's the answer, isn't it?
Oh.
And that 9. Now hold on. Let's. I don't know. Let's do a reality check here. Count the boxes. Each box is a 1 by 1. So 1, 2, 3, 4, 5, 6. That's pretty much 7, right? This one and that one, they kind of all look about, that's about 8, and actually it'd be a little bit more than 8, but these two together would be a little bit less. Yeah, that looks almost like 9.
Wow.
It's exactly 9, actually. So that's pretty interesting. Go ahead and let's take a couple minutes, since we've got all kinds of class time. As a table, take care of 3 and number 4, and see what you can get. Work together.
How would you do the antiderivative of a fraction?
You mean you've got x squared over 2? Just rewrite it as 1/2 x squared. Good question. feel free to talk about it as a table.
That's what he got there. I did that one, I don't know if you know that.
That is not right.
Or that one.
What's your number here? What is this?
That one was the first
10.5?
Yeah.
That is not correct.
Exactly.
Alright. Class, I want to talk about something strange that you might find with number 3. Okay? Emily, what did you get?
A negative number.
She got a negative number. For area, everything you have ever learned in geometry always told you area is going to be a positive. I will tell you this though. What is the mechanism by which we are calculating that area?
Limit.
Concave.
It's the limit.
Yeah.
And it was always this little width times that y value, right? And then this little width times this y value, right? And then you add them all up. Well, in these cases, what are these y values? They're negative. So it's going to be a negative number plus another negative number plus another negative number, which is just going to end up being a very large negative number. So actually, if your curve is below the x-axis, then this area right here will have a negative value. Okay? And if you apply the antiderivative, you will get a negative number. Alright? So, just real briefly, a couple of you I told that you need to rewrite that as 1/2 x squared. So what was the antiderivative that y'all had from that? 1/2 x cubed over 2? Okay, that 1/2, I agree that you're right up there. You're correct on that. And powering up to 3, that's good. However, you then need to divide this by 3. So if you want to, you can divide it by 3 right here, or you can multiply it by a third, or you could just turn that 1/2 into a 1/6. It's up to one of those. Plus, how would we turn that antiderivative of 4x would be 4x squared
Over 2
over 2.
plus 3x over 1.
Okay, so we're at 3x. Okay? That's a pretty squiggle. Evaluated from x equals -6. I just told you I was gonna do it right away. But anyway, there you go. I'm gonna leave this part right here as your homework. Okay? Going from here all the way down. Okay? But let's look at number 4. What do you notice about the region there on number 4?
Part of it's below and part of it's above.
Part of it's below the x-axis, part of it's above. Which means that this part right here is going to yield you a negative number, and this part right here is going to yield you a positive number. So when we find the integral of the whole entire region, this part here is basically going to cancel out a little bit of this number right up here. Okay? So if you're like, oh no, the area is 1, 2, 3, 4, you know, this one, if you're to do an approximation, 1, 2, 3, 4, this one is about 5, 6, 7, this one is about 8 altogether, then 9, and then 10. You figure it's probably going to be around 10, but instead you come up with a number that's like 7. See what I'm saying? Then that's actually a good answer, because it would be something like there's 7, or there's there's 7 over, there's, well, if you counted that, I just counted that as positive. The thing is, you have to count all this over here like as this is 7 and this is 3, and then you would subtract it, and actually you're gonna put like a 4. That makes sense.
Mhm.
Hold on. So how many did I count over here? 4, 5, 6, 7, 8, 9. So if you count like 9 over here and like 1 over here, you might think that the answer would be 10, but in reality the answer would be 8.
Negative 9 plus a negative 1 is 8.
Negative 9 plus a negative 1
Would be negative 10.
is equal to negative 10, okay? That sentence is true, but it has nothing to do with that, okay? Alright, because this region here is above the x-axis, so it would be a positive. This region right here is below the x-axis, so it would be negative. Okay? And so, I'm just going to pretend like we didn't see that. Let's skip through the rest of the homework, and let's see if there's anything that looks strange to our eyes that we are worried about. Number 5, that looks fine. Is number 6 okay? It's got some wings or some ears, but I think that we can still. Can you take the antiderivative of 2x squared plus 4x minus 2?
Yes.
Can you evaluate it at 1 and negative 3? Can you find the difference of those values? Sure you can. What about number 7? Can you take the antiderivative of that?
Yeah, I think so.
We did it before. If you remember, we rewrote this exponent down there as 5x to the negative third.
Oh, that's right.
That 5 is a constant multiple, so we're just going to keep it right out there. And then
X to the negative 2
x to the negative 2.
over negative 2.
Yep. And we'll evaluate that from 1 to 4. Okay? I think that's manageable. I don't know why this is. I'll leave the algebra to you.
Oh, there's some like cosine and sine one over here, some truth.
Okay. Do we need to discuss, before we go there though, this is the rational exponent. Do we need to discuss that? Okay, we can do one of them, that's fine. We did the antiderivative last week, so that negative 4 is just going to stay out front. It's a negative 4 multiplier. So Chloe, what's my new exponent going to be? 4/3. You keep doing the fractions in her head. Now, if you wanted to, you could say divided by 4/3, right? But we said, we're calculus students. We know that when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So reciprocal would be 3/4. Evaluated from negative 4 to 1. And you get some nice things because those 4's cancel. You know how to key this into the calculator, right? The 4 would be. Okay, so it wasn't that long of a diversion. Plus, how will we check our answers just to see if we're anywhere kind of in the right region?
We can. Oh, you mean check the whole answer? Or
Check,
the
just check your
at the
final
end?
answer. You know, if I say the answer here is 12.
We can look at the graph and use the pre-calculus.
Plug it into the
Okay.
function.
Plugging into the function is not necessarily gonna help out in this case, because plugging into the function is gonna tell me this value or this value and this value. If you wanted to, you could go all in and do a literal, like find this rectangle and this rectangle. You can do that. I would suggest an easier method of checking your work just by counting boxes. Okay? Okay, each one of these boxes is 1 by 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This one, probably about 12 together. So 13, 14, 15, 16, 17. This one, these two together is about 18. That's 19 right up there. Okay? And then this is going to be -1, -2. This one together maybe probably about a -3. So I would guess my answer is probably going to be around 16. If you get something that's in the 50s, then you might need to go check your work. If you get something that's negative, probably need to go and check your work. All right. And same kind of thing. Ooh, an e to the x. Mr. Goddard, you didn't tell us what the antiderivative of e to the x was.
It's e to the x.
It's e to the x.
Oh,
because the derivative of e to the x is e to the x. So this is going to be, so the antiderivative of -3 e to the x is?
-3.
-3 e to the x. Yeah, okay, so how about that? Isn't that awesome? There you go, there's that one too. That's a great problem.
Oh, what about the one that's evaluated at pi over 2? Oh, that.
Ooh, okay. First off, make sure your calculator or Desmos is in radian mode if you're going to be doing this. If you don't know how to convert Desmos to radian mode, there's a little wrench up in the corner. You click that wrench, and that'll make sure you're in radian mode. You're either in rad mode or deg mode. Do you need to see this?
Yeah.
Okay. At least you're honest. It'll take 5 seconds. 5, 4, 3, 2, 1. There you go.
Wow.
That's it right there. Okay, just make sure, because sometimes the default is in degrees. So.
Okay. Thank you.
You bet. So now all I need to figure out is what is the antiderivative of cosine?
Negative sign.
Oh, y'all are so cute when you're wrong. The antiderivative of cosine is
It's
not
sine.
negative
It's
sign,
just
it's
sine.
just
If it
sine.
was
The
just-
derivative of cosine is negative sine, but the antiderivative of cosine
It's sine.
is just sine evaluated from 0 to pi over 2. So, this is going to be sine of pi over 2 minus the sine of 0. Now, I happen to have I don't have it memorized, so to speak, but I can draw the sine graph just off the top of my head. I know that sine starts at the baseline, at 2 pi, it ends at the baseline. I know right in the middle there, it's on the baseline. Sound familiar? Same, that old song. And I know that at pi over 2 it goes high, and 3 pi over 2 goes low. I know it kind of looks like that. So I don't even need Desmos. I know that sine of pi over 2 is 1. And I know that sine of, that's supposed to be 0, not theta. Sine of 0 is 0. So I'm pretty sure the area there is 1. And you're like, oh no, Mr. Goddard, no way, because that box right there, that's, no, okay, now look at your axes now, right? Okay, 1 is all the way up there. This is a half. This is,
Quarter.
yeah, something like that. Like that. Well, this is pi over 2, so this is around a little bit, like it's like 1.6, so this is around 0.8. So yeah, that's not, this box right here is not a 1 by 1 box. But the area under that curve is 1. Which that's pretty cool, I think, that it kind of cancels it out. least I think it's 1.
Seems right.
Oh yeah, it's 1. Let's glance very quickly at the rest of those. We should have done that. We need to give you homework answers. Mr. Goddard from last year would be chomping nails. Alright.
Kuchika. Wow. It's all coming along today, man.
Oh no, that one's kind of cool. You'll never guess what 15 is.
Wow.
Yeah.
Okay, well.
Oh, actually, it could be 0.
Cause they both cancel out because it's the same proportion. Wow.
Maybe, I don't know.
It's like
That would be a good thing to check, though, not just, sometimes things aren't what they seem. Sometimes they are what they
And
seem.
it goes from 0 to negative 5.
You know the old saying, don't judge the integral of a trigonometric function by its graph.
What?
Don't they say that nowadays? Antiderivative secant squared, you know what that is, right?
And, yeah, it's
It's whichever one of those things, and when
Yeah.
you take the derivative of it, you get secant squared.
sine cotangent, right?
And you can look back at your chart, it's also in the front of your book.
It sounds like it's.
It's literally, you know, there's 6 things that you know the antiderivative of when it comes to trig.
The
All
only
the
one
rest
you
of
can't get
it.
is tangent, right?
So, well, I don't think you can't get tangent by itself, secant by itself, cosecant by itself, cotangent by itself. Like there's those other 4 you can't. Tangent, cotangent, secant, cosecant. You can't get those by themselves. They're either squared or combined with another trig function. So.
Yeah, because there's no like derivative that gives you cotangent or something.
Right. This one's yeah. So, okay. Wow, we have learned a whole lot today, haven't we, class? Actually, I feel like we've done more algebra than we've learned. But anyway, we learned the antiderivative of a function from A to B is equal to the antiderivative value of B minus the antiderivative value at A. Hold on, Hector. I want to talk about the rest of this week. So Thursday is going to be the day of red, the day of all grading. Everything grading is going to happen on that day because Wednesday, you know, there's some things that we haven't actually graded yet. Those 2 things that you gave me, Chloe, great job, but we haven't graded them yet. We're grading everything on Thursday in preparation for our quiz on Friday. Okay? Because Wednesday, y'all are going to be going over your ASVAB answers, I think, or something like that, your results, whatnot. So I'm not even going to see you, which is actually a great day because I'm administering a STAR test on that day anyway.
Oh.
So, that means it's only today and tomorrow. And tomorrow, piecewise functions in the area between the curves, we're going to look at that.
And that's it.
And then this is next week. I actually decided to put it down here so we can see. So Monday we're gonna do our we'll correct that quiz, okay, and we'll do any review necessary. Tuesday I'm not going to see you because it's just the odd. Well, most of you that are in my classes like 20 times a day I'll see you, but you're not going to see for calculus. Odd numbered classes on Tuesday, even numbered classes on Wednesday. Exam period lengths are an hour and a half.
I literally see Mr. Butter every day for evens.
2,
2,
yep,
4,
and
6.
4 and 6. That's right. So some other people are not so lucky. Anyway, and then the house party half day, and I can't believe we're done. So this Friday's quiz is going to be everything 5-ish. So antiderivative, area under the curve. There wasn't a homework on the crazy limit of the sum. Okay, so you're not going to worry about that.
Oh yeah.
But this is fair game, and tomorrow's stuff is fair game, and all of it's going to be due on Thursday. We're just going to have like a free answer keys laying around. Grade as much as you have. Have your cheat sheet out. Get your cheat sheet prepared and stuff like that. So that's what Thursday's going to be. I'm not teaching. I'm mostly providing that those options, and then your final exam will be a legitimate multiple choice. Everything in the semester beast of a test.
Holy
Okay?
cow.
So it's not just this. It's not fair for it to be just over this most recent stuff because you might be rock solid on all the earlier stuff. So it's going to be a little bit of limits, a little bit of derivatives, a little bit of all the other type of derivative stuff that we had, chain rule, quotient rule, a little bit of this stuff too. Okay? So.
That's no good.
All right, you gotta have at least one final exam where it's literally a final exam, okay?
Well, we have
on all these other teachers having projects and stuff like that.
Do you think we're gonna have one, or yeah, we probably will next semester? Or-
You'll have a final exam next semester, absolutely. And by that time, you'll be super excited because you're about to walk
and so we won't be thinking about having
right. So, well, college classes end like 3 weeks before
Oh, that's true.
graduation. Although graduation is super early this year.
Really?
Now, yeah. Anyway, but other thing is,